in 3510, you should have covered z-scores and single sample t-test. Is that correct? You did z-scores for x, right? Where you're looking at standard, so you're calculating z, and you're trying to figure out, a z-score of 1 is 1 standard deviation away from the mean, right? A z-score of 2 is 2 standard deviations. And if it's positive, that means it's above the mean. If it's negative, that means that it's below, right? Sound familiar? Then you did calculations for z-score for a sample mean, where you were looking at samples of a particular size, right? So for all samples of size 10, we can calculate the standard error, right? And say how far that sample is from the mean of all samples of that size, right? Remember that? Sound familiar? These formulas should look familiar. Then you did single sample t-test, where now you don't know the population standard deviation. So you have to use the standard deviation for the sample to figure out the estimated standard error, right? You can't actually calculate standard error anymore, it's estimated standard error. Does this sound familiar? Vaguely? Okay, so these are the formulas that you learned last time. And what I've done is break down like what's in the denominator each one, giving you the formulas so you can see where those values come from. Other important calculations, I've given you those formulas. And this is all just review stuff, right? These are all things that you should be familiar with. When we calculate effect size for z-scores, we can use Cohen's d or r squared, right? Sound familiar? Okay. And in case you don't remember what the different symbols stand for, I put some notes over here. Now what we're going to move on to now are the t-tests for 2 samples. This is where we don't know anything about the population at all. And we're going to compare either 2 independent samples, so that's between subjects comparison, where we've got 2 samples that come from different populations, or we're going to do related samples where we're comparing the same group to itself, like before and after, or we're having them do different things and we're counterbalancing. Okay. Now, if you look at the z-score formula, the ones that you have, and the single sample t that you've seen before, you see there's a pretty general pattern, right? You've got a mean minus a mean, right? A sample mean minus a population mean over a standard error, right? And up here, it was a score minus a mean over standard deviation. Now we've got a mean minus a mean over standard error. Here we've got a mean minus a mean over estimated standard error. So it's some mean difference over some measure of variability. And that's common for all of those. That pattern holds true for the 2 types of statistics we're going to learn in this unit, the independent groups t-test and the related groups t-test. For the independent groups t-test, we're going to use the means for the 2 samples, right? We have 2 samples. So we're going to have a mean for sample 1 and a mean for sample 2. And then we're going to calculate a kind of estimated standard error based on the standard deviation for the samples that we have. For the related groups t-test, we're going to calculate the mean difference of the scores for the sample that we're testing. We're going to get their mean in condition 1 and their mean in condition 2 and calculate the difference. And then we're going to divide it by an estimated standard error that's calculated from those different scores. So the pattern is the same. The formulas are all related. Right? It's always a mean difference over some kind of standard error. That will help. When we take the test on this unit, I do not give you the formulas. Okay? You are responsible for choosing the formulas you need to do the calculations that are required and putting them on your note card. So I encourage you to make sure you're familiar with the differences in the formulas for these 2 things, and that you keep track of which formulas from up here and the rest of this handout you also need. Because if you don't remember how to calculate some squares and I ask you to do it, even though that was from 3510, you better know how to do it. You need to have the formula on your card. So this is just an overview to show you the connection between the different tests that we're doing. Yeah?
So since the t-tests were two independent samples between the t-tests were two within
That's right. Exactly right. If you have a within subjects experiment with two conditions, that's going to be this one. If you have a between subjects experiment with two conditions, it's going to be this one. Yeah, exactly right. So you want to have this, what we all really need is like a big table in front of us because we're going to pull out all these handouts. But this will give you a lot of the formulas that you're going to need. Okay. Now the other things you have over there, we have our critical value table. Now it says on here, do not write on the pages in this packet because this is an example of the one that I used. I generated this for use on tests, but because our textbook doesn't have all the critical value tables that I want you to have, I'm giving each of you this packet. So this is yours to keep. You can bring it out in class and use it. Okay? You'll get different pages on the day of the exam, separate ones, clean ones. So if you want to write all over these, you actually can. But you'll get a packet that looks just like this for the test. Okay? That has the critical values. So you want to make sure you bring this to class every day that we're doing stats stuff. And from this point forward, you want to make sure you have a calculator in class because you're not allowed to use your phone as your calculator in here, and you're not allowed to use your phone on the test as your calculator. So you want to make sure that you have the calculator you plan to use on the test so you're familiar with it and how it works. Okay, so this we'll pull out in a little bit. This handout right here is a general overview for this test. The first test we're going to learn, the t-test for independent samples or independent groups, or the between subjects t-test. Okay? This is a general overview that kind of explains the test to you because we don't have a separate statistics book. It has the different formulas in it that we will use and talks you step by step through doing the calculation. It also has information about effect size, like if you don't remember things for Cohen's D, like what counts as a small, medium, or large effect, that stuff is all in this brief overview also. This is the bulk of the background I'm going to give you on this test. I am not into like all the extra stuff about each statistical test. I want you to know how to do it, and I want you to know when to do it. So our focus in here will be on learning the steps and thinking through solving problems rather than me lecturing about statistics, because who wants to hear a lecture about math? You need to just do it, right? That's what you got to do. So you're going to have this one over to the side. You'll use it as a reference as you go through problems. What we're going to do right now is we're going to learn about independent groups t-test by doing an independent groups t-test. Okay, that's how I teach stats. I'm not going to describe each of the formulas to you until we get to a place where we need it. So you'll want to have a piece of paper out. We're going to be doing calculations today. If you didn't bring your calculator today, I will give you a one-day dispensation to break out your phone and use it as your calculator, but after this, you won't be able to do that, okay? But you do need to have your calculator to do math today. Okay. So everyone should have this sheet out and some paper to write on. The idea here is that an educational psychologist is doing an experiment to see if children will read longer. You're trying to get children to read. And you need them to practice because reading's hard. So will children read longer if they're reading a story where one of the characters has their name? Okay? So they can identify with the character. So for example, if Abby were in this study, one of the characters in the book would be named Abby. Okay? So would Abby, as a child, like to read a book more if one of the characters, particularly one that she liked, was named after her, right? That's the idea. So the researcher has two groups of kids. Okay? It's independent samples, right? Two totally separate groups of children. Okay? They're all the same, about the same age and about the same level of reading skill. And they've been randomly assigned into their different groups. Okay? And what we have here are data for one group of children that read the modified story. That's the story where the characters in the book are named Anne, Boris, Clyde, Dana, Eric, and Fiona. Okay, so those are the characters. So every kid in that sample has a character in the book named after them. And then we have the children over in this group who also read a book about Anne, Boris, Clyde, Dana, Eric, and Fiona, but none of them have that name, right? So they're reading just a regular children's story, not a story with their name in it. And the researcher gathers data about how long, in minutes, the children read the story before they put it down. Okay? Now this is obviously not a very long book, right? If a child can read it for 4 minutes, right? So this isn't a chapter book or anything, it's a picture book. But the idea is the researcher wants to compare to see if the children in the experimental group, that's the modified story group, if the children in that experimental group read for a significantly longer period of time than children in the control group, who are reading just the ordinary story for them, right? It's just a children's story with characters that don't have names that match theirs. Does that make sense? Do you understand the layout? What's happening? We're just comparing two groups. So the first thing I want you to think about as you're doing this particular statistical test is what hypotheses are you testing? So first, I want you to identify the null hypothesis and then the alternative hypothesis. And when we do this in this class, you want to answer several questions in that hypothesis. Okay? Now the easiest thing to say when it comes to a null hypothesis is what? What's the super short form of the null hypothesis?
Nothing happened.
Nothing happened. There's no difference. It doesn't matter, right? But that's not very informative to somebody who's trying to understand what the person is doing in their study. Because if you just say the null hypothesis is nothing happened or it didn't matter. Well, what didn't happen and what didn't matter, I don't know. Okay? So when you generate a hypothesis in this class, and I'm going to write on here because I don't really have a lot of board space. All right, so let's see if I can get this up here. Okay. You want to include several pieces of information. First piece of information has to do with what groups are being compared. And that's information about the independent variable. So what groups are we comparing? We're comparing children who read a story with their name in it and children who read a story without their name in it, right? That's who we're comparing. Those are the groups that are created by the levels of the independent variable. All right. Next thing we're going to make sure is in our null hypothesis is what is being compared about the groups. And that's about the dependent variable. So what are we comparing about them? We're comparing how long they read in minutes. The next thing you want to make sure you know is, are you predicting a significant difference or not? Predicting a significant difference or not. In the case of the null hypothesis, the answer would be no. Right? You're not predicting a significant difference. And if you are predicting a difference, this will come up with the alternate hypothesis in a minute. If you are predicting a difference, then you need to indicate the direction of the effect, if any. So, and then there's kind of a fifth one, and that is that you need to be clear. Is this a between subjects or within subjects comparison? Okay, so your wording needs to be very clear. So let's try this. We know we have a null, there's both the null hypothesis. So how could we include all of this information, all the relevant information, in that null hypothesis? The researcher predicts that children who read a story with their name in it will not read any longer than children who read a story without their name in it. Okay? So I've included all the important information. From that null hypothesis, I now know what groups are being compared, what's being compared about them, and that I'm not predicting a significant difference. Now you can do it a couple different ways. You could say, there will be no significant difference in the amount of time children spend reading. Right? We talk like that. So children who read a story with their name in it will not read for a significantly longer period of time than children who read a story with their name in it, or without their name in it, whichever one. Okay. So you want to make sure you include all of the relevant information when you come up with a null hypothesis. Now, if we do the alternate hypothesis, the researcher is predicting a particular effect, right? The researcher thinks that reading a story with your name in it is going to make you read for a longer period of time. So if we did an alternate hypothesis, how could we do it and fulfill all of our requirements? Anybody want to give it a shot? Yes?
Children who read a story with their name in it will read the story longer than children who read a story without their name in it.
Right. So children who read a story with their name in it will read for a significantly longer period of time than children who read a story without their name in it. Yeah. Now, that's important. That wording is important because it makes it clear that you're comparing two groups of children. And that matters. Because it's possible you could do this as a within subjects design too, right? You could have children read two stories. One story that has their name in it, one story that doesn't have their name in it. You could totally do that. And you need to be clear when you state the hypotheses that you're testing, what kind of comparison you're doing. Is it a between subjects comparison or within subjects comparison? So null hypothesis, there will be no difference in the time spent reading for children who read a story with their name in it versus children who read a story without their name in it. Alternate hypothesis, children who read a story with their name in it will read for a significantly longer period of time than children who read a story without their name in it. Yes?
So how would you get rid of within subjects? Would you say children who read a story with their name in it first, or would it be like
Well, you're going to counterbalance it, right? So you'll have some of them read the story with their name in it first, and some of them will read the one without their name in it first. So you would say something like, children will read for a significantly longer time when they read a story that has their name in it than when they read a story that doesn't have their name in it. Well, we'll practice that next time. First we're going to do independent groups, and then we'll do related groups right after. Okay? All right. So does anybody have any questions about those 5 things? Make sure when you write out, if I ask you for a hypothesis, you include all the relevant details. Okay. All right. So now next question. Would we do a one-tailed test or a two-tailed test? And how do you know? one-tailed test or a two-tailed test? And how do you know? Yeah.
Does that have to do with non-directional direction?
It's exactly right. It has to do with whether we're making a directional prediction or a non-directional prediction with the alternate hypothesis. So, what's a directional prediction? Yes, Zach.
Is that when you're assuming that there's going to be an increase or decrease?
Right. But it couldn't just be either one, right? So if you take a look at that packet, you're doing a one-tailed test when you're predicting that the scores for the experimental group are going to be in one tail or the other. Like Abby said, it's either going to be a positive difference or a negative difference. But it's not that you think it could be either one. It's that you're making a specific prediction about the direction of the effect. A two-tailed test is where you're not sure. So it's a non-directional prediction. All you're saying is that you think that the two groups are going to be different from each other, but you're not making a specific prediction about how they're going to be different from each other. You're not saying you're pretty sure that one's going to be bigger than the other. You're just saying you think they're going to be different. A one-tailed test gives you a bigger zone here, all in one end, right? So if you're doing an alpha of 0.05, that means 5% of the 5% of the distribution is all bunched up in one end of the distribution. That's your target area, your critical region. So you've got this nice big zone to try and hit. But you're also completely ignoring half of the distribution, right? You're so sure that it's going to hit in that big zone that you're ignoring half the distribution. If you're doing a two-tailed test, that same 5% gets divided over both of the tails, right? So you have 2.5% in one end and 2.5% in the other end. So you've got smaller targets, but you're looking in more places. So given that our alternate hypothesis in this case is that children who read a story with their name in it will read for a significantly longer period of time than children who read a story without their name in it, which one do you think we're doing? One-tailed. Yeah. We're making a specific directional prediction saying that we think that experimental group's time is going to be higher on average than the one for the control group. Okay. So we're doing a one-tailed test. So it says, given an alpha level of 0.05, what t-score will define the boundary of the critical region for our hypothesis test? In other words, what is the value of t critical? And what do you need to look up this value? Well, we've got t distribution. Great. So let's look and see what kind of stuff we need to look this up. We look at our table. Looks like we need to know some degrees of freedom of some kind, right, over here. We need to know that the alpha, which is up here, right, that's the proportion in one tail. And we need to know whether we're doing a one-tailed test or a two-tailed test. Okay, so there's three pieces of information we need in order to look up a critical value for t, or t critical. We have to know the proper degrees of freedom, whether it's a one-tailed test or a two-tailed test, and what our alpha is. Now the default alpha in this class, unless otherwise specified, is 0.05. So you can always, if you're taking a test or working on a problem, and I don't specifically tell you what the alpha is, go for 0.05. If I say the alpha is something different, then use the alpha that I said. But the most common alpha in psychology studies is 0.05, so we'll just practice using that one, okay? So we've already decided that we're doing a one-tailed test. We've already decided, because it says here in the problem, that alpha is 0.05. So we know we're going to be looking somewhere in this column, right? Somewhere in that column. Now the question is, what degrees of freedom is the right degrees of freedom to use for an independent group's t-test? Well, as it turns out, the right degrees of freedom to use is what we call degrees of freedom pooled. Okay? Which I write DF with a little p subscript. Degrees of freedom pooled. Degrees of freedom pooled is the degrees of freedom for sample 1, so DF subscript 1, the degrees of freedom for sample 1, plus the degrees of freedom for sample 2. You guys remember how to get degrees of freedom for a t-test? N minus 1, that's right. So degrees of freedom 1 is N minus 1. Okay, so if I'm doing degrees of freedom for group 1, I take the sample size for group 1 and subtract 1. If I'm doing the degrees of freedom for group 2, I take the sample size for group 2 and subtract 1. Okay? Super easy. So if we take a look at our problem, we see that how many kids are in each group? 6. Okay? So that means that our degrees of freedom here is 6 minus 1 for group 1. So that's 5. And also true for group 2. 6 minus 1 is 5. So that means degrees of freedom 1 plus degrees of freedom 2 is 5 plus 5. It's 10. Make sense? Now, we have to do these separately because in an independent groups test, it's possible that the groups could be different sizes. It's 2 separate samples, right? I could have, 6 kids in one group and 7 kids in another group. Because they're different groups of kids. Could have some issue with attrition or something like that. Could start off with 10 kids in each group and then some kids drop out for some reason, or something like that. So we calculate the degrees of freedom for each group separately and then we add them together. We pool them to get a degrees of freedom that reflects both of the samples being used in the study. So we need degrees of freedom 10. So now we come back here to our chart. Okay. Degrees of freedom 10. So I'm going to come down here, find degrees of freedom 10. And I'm going to move over to the column that's for alpha 0.05 in one tail, that middle column, and I get 1.812. Now, our alpha that we're using is 0.05, so that's out to 2 decimal places. Because we're using an alpha with a precision of 2 decimal places, we're always going to round all of our calculations and our critical values to 2 decimal places also, because we don't want to have numbers that are more precise than the alpha that we're using. Okay? So 1.812 gets rounded to what? 1.81. Okay. So we can now say that our T critical, is positive 1.81. And the reason I say positive, the reason I'm marking it, is because this is a one-tail test, and I'm indicating by putting that plus in front of it that I'm expecting the observed value to be in the positive tail. If I were doing a two-tail test, the critical value would have plus minus in front of it, indicating that it could be on either side. So if you have a one-tail test, you should mark what the prediction is. If you're making a positive prediction, put a plus in front of it for the critical value. If you're making a negative prediction, put a negative number in front of it for the critical value. Okay? If it's a two-tail test, put both. Do you have a question? No? So positive 1.81 is our critical value. Okay, next question. Now we have to calculate stuff. Okay, part of these calculations we've already done. But we're going to start off by calculating degrees of freedom, mean, sum of squares, and sample variance for each sample. For each sample. So we've already done the degrees of freedom for the 2 samples, right? We had to do that to figure out the pool degrees of freedom. So we already know that the degrees of freedom for our 2 samples are 5 and 5. What about the mean? So I would like, here's what we're going to do. I'm going to have the people on that side of the room. You guys are going to do modified story. People on this side of the room, we're going to work on the ordinary story. Okay? So tell me, for your assigned sample, calculate the mean for me. So I need a mean for the modified story group.
I got 10.33.
10.33? We agree? Okay. Okay, and for the ordinary story group? 6. All right, round numbers. All right. Now, next question. Oh, gosh. Sum of squares. How many people remember how to do sum of squares? Yeah, you're raising your hand like you remember, or you have a question?
No, I remember.
You remember? Good. Okay. I'll know. All right. So let's do the sum of squares for the modified group together. Okay. And then we'll see. And then I'll have you guys do the ordinary group. Okay. I'm gonna break out some new paper here. All right. So sum of squares. The sum of squares, that stands for the sum of squared deviations. All right, that's what that stands for. The sum of squared deviations. And a deviation is the difference between any given score in a set and the mean for that set. So we're going to have to figure out the deviation for every score. And then we're going to have to square them, and then we're going to have to add them up. That's where we're going to get sum of squares. So if we're starting with the modified story, I've got Anne, Boris, Clyde, Dana, Eric, and Fiona. It's almost like I planned it that way. I know. Pretty slick, huh? All right. So the first thing we need to figure out is the deviation for each child. So that's going to be x minus the mean. Okay? So Anne, her score was 4 minus 10.33. What does that equal? What's 4 minus 10.33? Okay. Negative 6.33. So this number right here is Anne's deviation. That's her deviation. Now Boris, 16 minus 10.33. What's his deviation? 5.67. Good. Rounding to 2 decimal places. And make sure you pay attention to whether it's negative or positive, because you want to be clear. Now, Clyde. Clyde is 11 minus 10.33. What's his deviation? 0.67. Dana. What's Dana's deviation? 9 minus 10.33. Negative 1.33. And Eric. 8 minus 10.33. Negative 2.33. And Fiona, 14 minus 10.33 equals 3.67. Okay, so we figured out the deviation. Now, if you do this, in a problem set, whatever, I'm fine if you just put these numbers. You don't have to put that math. But on a test, I encourage you to, I will say, show all your work. I want to know where every number came from. So it's good to get in the habit of writing everything down. You're like, oh, but my calculator just remembers everything for me. But here's the problem, is that on a test, if you just put down the answer and don't show me all your work and you're wrong, I have no idea where that wrong answer came from. So you want to get in the habit of putting all your work down, every single step. Because then if there's an error, it's easy for me to find and then we can fix it. And that's important. So now we've got all of our deviations. Now we need to square these deviations. Okay. So what's negative 6.33 squared?
39.7.
To two decimal places, it's 39.70.
Oh, it's 0.69.
0.69. Okay. So say that again, 39.69. Okay. And what is 5.67 squared?
32.15.
Yes? Do we agree?
Somebody got something else there, right?
It should be
40.07.
Okay.
But the first one.
This one should be something else.
Yeah.
Okay, this is why we do math by consensus, because if one person shouts out a number and it's not the right answer, and everybody just writes it down, what happens? Then you're all like, what? Where'd that come from? Okay. So let's get rid of that. And what's the answer we want to put here instead? 40.07. Okay. So see, don't be shy. You're fighting for your math rights. Okay, 40.07. Then 5.67 squared is what? 32.14. 15. Rounding up. Okay. 32.15. My math choir. Love my math choir. All right, 0.67 squared.
0.45.
0.45. And negative 1.33 squared.
1.77.
Wait, no, I'm sorry. I got it. Dyslexic.
Yeah.
1.77.
Yeah.
All right, 2.33, negative 2.33 squared.
5.43.
5.43.
Yes.
3.67 squared.
1.35.
Huh? What? No, 3.67.
Oh, 3.67.
3.67. It's got to be closer to.
Oh, 13.47.
Okay, I'm like, what? I'm pretty sure 3 squared is never going to be 1. Okay, so, no, that's good. Because this is why everybody says it, and that way if you had something wrong, you fix it, right? Because everybody needs to have the right answers on here. Okay, so now I don't remember what you said. 13.47?
Yeah.
Okay, so everybody knows where each one of those numbers came from. Okay, now, we got all those numbers. Now, we're going to add them up. So add up those square deviations. So add 40.07 and 32.15 and 0.45 and 1.77 and 5.43 and 13.47 and tell me what you get.
Yep.
93.34? You agree?
Yep.
Math by consensus. We vote and we say it's 93.34. Yep?
Yes.
Okay. So that's our sum of squares for that group. Right there. That's the sum of squares for the first group. Now, I would like you to do the same thing for the second group. Okay? You've got a model to use now, so go through and do it for the second group. Javier's loving this because he doesn't have to do it. So try it for the second group and tell me what you get.
Will we not use the degrees of freedom pool variance?
We will use the degrees of freedom pool to look up the critical value. We will also use it in subsequent calculations to calculate the pool sample variance. So you need to know how to get the pool degrees of freedom. We won't use the independent degrees of freedom for the individual ones. We don't use those for anything. Double check. Your neighbor's done. Check with your neighbor, see if they got the same answer you did. If not,
Oh, that's what they want.
did you find it? Okay. You got it? What you guys, anybody got it done? 28? 28 even? Isn't that nice? Don't you like how I gave you the easier one to do on your own? Wasn't that nice?
I appreciate it.
Yeah, sure. I figured we might as well do the hard one together and then do the easy one when you practice. Okay. So now we figured out that the sum of squares for our first group is 93.34. The sum of squares for our second group is 28, right? Now we want to do the sample variance for each one. Do you guys remember how to do sample variance? You're gonna live and breathe this particular formula all semester. So just want to remember, sample variance is sum of squares over degrees of freedom. So sum of squares over degrees of freedom. So if you're talking about the sample variance for sample 1, that's going to be the sum of squares for that first sample over the degrees of freedom for that first sample. So that means 93.34 over 5. What do we get? 93.34 divided by 5 gives us what?
18.67.
I have a vote for 18.67. I see some head nods. All right, 18.67. And then if I want to do the sample variance for the second sample, that's going to be sum of squares for the second sample over the degrees of freedom for the second sample. So that's going to be 28 divided by 5. And what do I get for that?
5.6.
5.6 even? Okay. So we should now have 18.67 and 5.6. Yes? All those numbers match? Everybody agrees? Everybody knows where they came from? Yep. If at any point while we're doing math in here, we put up a number and you don't know where it came from and you're not sure how we got it, say stop. Do it again. Explain to me again. Because I want, when you go back and look at your notes, I want you to know where every single value comes from. And don't shortcut your notes. Be detailed. Because you want to be able to go back and tell from what you wrote how to do it again. Okay. So that was 4A. We've calculated the degrees of freedom, the mean, the sum of squares, and the sample variance for each sample. Okay. Now we're going to calculate pooled degrees of freedom, pooled sum of squares, and pooled sample variance for the two samples combined. Now, we already did the degrees of freedom pool, right? Degrees of freedom pool was degrees of freedom for group 1 plus degrees of freedom for group 2. That was easy. 5 plus 5 was 10. No problem. Now, to get the sum of squares pool, we're going to do the same thing. We're going to take the sum of squares for group 1 and we're going to add the sum of squares for group 2. So that means we're going to add now 93.34 plus 28. And what does that give us?
121.34.
I have a vote for 121.34. Yes? Now we're going to calculate the pooled sample variance. Pooled sample variance. And that's written S, little s, superscript 2, subscript P. Pooled sample variance. Okay? And the formula for pooled sample variance is really easy. Remember we said up here a minute ago? Sample variance is sum of squares over degrees of freedom. Pooled sample variance is pooled sum of squares over pooled degrees of freedom. Make sense? So now we know that it's 121.34 over 10. And what does that give us? 12.13. Everybody okay with where that came from? Mm-hmm. All right, just checking. Don't want anybody to get lost. Because what's going to happen is we're going to work through one problem and then I'm going to go do problems. Okay? There's problem set and additional practice problems, and all you got to do then is just practice and do it and do it and do it. Okay? Go through these steps. Next, we're going to calculate the standard error for the two samples combined. So we need to have some standard error-y thing for our denominator for calculating t. So we have to do a standard error. And that looks like that's our standard error and our formula for the standard error. Okay. Now it looks scary, but if you look at your sheet, remember this one? What we're trying to do is get the denominator that we need, okay? Before we use standard deviation, then we did estimated standard error, then we did standard error, then we did estimated standard error. This is the one we're doing now, okay? This is the denominator. This is estimated standard error for pooled samples, okay? Or the pooled estimated standard error. But if you look at it, if you compare it to the previous formulas that you've used to calculate standard error, it's pretty similar. It's just now we're going to use information from two samples instead of from just one. So our formula is the square root of pooled sample variance over the sample size for group 1 plus the pooled sample variance over the sample size for group 2. Now, what you don't want to do, sometimes people do this, they make a mistake at this stage. Here's what they do. They say, oh, I get it. Don't do that. Okay? It's not add the sample variance to itself and divide by the two sample sizes together. Don't do that ever. No, don't do it. Okay? Make sure they're separate. Okay, make sure they're separate. So, our pooled sample variance was 12.13, correct? And our sample size for group 1 is not 5, that's the degrees of freedom, it's 6. Make sure you put the sample size there, not degrees of freedom. That's the next place where students often make a mistake, because they've been doing stuff with degrees of freedom, and then they write the degrees of freedom in there. Make sure you put the sample size. So what is 12.13 divided by 6? 2.02? Fortunately, those are both the same calculation, so once you do it once, you're golden. Okay? Now, so you're going to take the square root of those two things added together. If we add those two things together, I'm going to take a shot in the dark and say it's 4.04. Am I right? Okay, good. At least the cold medicine hasn't ruined my brain that much. Okay? So, what's the square root of 4.04? 2.01. Now, on a test, I expect you to write out all those steps. Don't just go, oh, pooled estimated standard error is 2.01. I'll be like, where's your math? Show your work. Show all the steps. That way, if you screw up here and put degrees of freedom, I'll know that's what happened. And you'll know that's what happened, and we'll be able to try and avoid it in the future. So make sure you show all the steps. Write everything down. And make sure you round at each step. Don't do all your calculations. Don't plug everything into your calculator and then round when you get to the end. Round at each step. That's the only way everybody will always get the same answer with everybody else. All right. So now we've figured out the estimated standard error for the pooled samples. Now we have to figure out the mean difference for the comparison distribution. Okay? The mean difference is mean 1 minus mean 2. That's the numerator of our T formula. So mean for 1 was 10.33, right? Is that right? From before? And the mean for group 2 was 6, correct? So what's 10.33 minus 6? 4.33. Right? Okay. So now we've got the numerator. And when we calculate T observed for an independent groups test, the formula is the mean difference over that estimated standard error for the pooled samples. So now we know that mean 1 minus mean 2 is 4.33, and the estimated standard error for the two samples combined is 2.01. So our T observed is what?
2.15.
We have a vote for 2.15.
I agree, yeah.
Yep. Okay. Let me note again. It's positive 2.15. Mark it to show me that you know that it's positive 2.15. Now, we think about our T critical and our T observed. Our T critical we had before was positive 1.81. That's what we decided last time, right? We looked it up. And our T observed is 2.15 positive, right? The relationship between these two things is like that. Make sense? This is a bigger number than that number. This is the alligator. Alligator always wants the bigger number. That's how I learned it in elementary school. So I always see those things with teeth. Is Pac-Man? It's a generational thing. We didn't have Pac-Man when I was a kid. It's a long time ago. But I like Pac-Man. Yeah. So Pac-Man always wants the bigger thing, or the alligator. Now, this is important because when we write out the APA style statistical statement for this analysis, we're going to have to indicate what the probability is that we would get this number. And the probability that we would get this number is less than 0.05, right? The probability of getting this number is 0.05. And the probability of getting this one is even lower because this is 1.81 and 2.15 is somewhere out here, right? So it's an even skinnier part of the tail where it has an even lower probability of occurring. If we lay this out for positive test, we should have the observed value outside and the critical value inside. And if you do it that way, then this symbol will be going the right direction to show statistical significance.
Can you repeat that one more time?
Sure. So when we're looking for something in a positive tail, the expectation is that the critical value will be on the left and the observed value will be on the right. Does that make sense? So set it up, write it out. Critical value on the left, observed value on the right, and then put in the proper symbol. In this case, the sign indicating that the observed value is greater than the critical value. If you do that, this symbol will be going the right direction for you to just copy it in a couple of minutes when you write out the statistical statement. Okay, you're going to need to know which way this is supposed to go. When this symbol is going this way, when P is less than whatever alpha was, this is statistical significance. That means you have statistical significance. If P is greater than 0.05, not significant. So if we retain the null hypothesis, P is greater than 0.05. If we reject the null hypothesis, P is less than 0.05. We okay with that?
One more time on that last part about the reject.
Okay. When we retain the null hypothesis, we're saying there is no difference between our groups. For that to be true, it means that our observed value was not out in the critical region. So it has a greater probability of occurring than 0.05. So when we retain the null hypothesis, this is how we talk about the probability of getting the observed value.
Okay.
When we reject the null hypothesis, in other words, the observed value was in the critical region, it was where we predicted it was going to be, then the probability of getting that is less than 0.05. And so whenever we have a statistically significant result, we're going to write it out like that, with P being less than 0.05. So we'll do, most of the tests we do, we're looking at positive tail. When we do a one-tail test, we're looking at a positive tail. So most of the time, it's going to be in this relationship. If you were doing a t-test and you were expecting a number to be more, the observed value to be more negative, you flip-flop it. You flip-flop it. So then you do t observed over here and t critical over there. Because there's your critical value, and then there's your observed value. So just make sure that you know whether you're looking in the positive tail or the negative tail, and that will help you lay this out so when you write the symbol, it will always be going the correct direction for significance or not significance. All right. So we now know that we've evaluated the null hypothesis. Are we going to reject or retain the null? Reject, right? We have a statistically significant difference. Okay. Good. Now we need to figure out the effect size. Now, effect size, we can do two ways. We can calculate using Cohen's d, or we can calculate using r squared. First, let's do it with Cohen's d. Okay? Cohen's d for independent groups t-test, or between subjects t-test, is mean 1 minus mean 2 over the pooled standard deviation. Now, this value on the top you should recognize because it's the same numerator as you used for t observed. That's still 10.33 minus 6. That's still 4.33. Okay? It's the exact same numerator for the t observed calculation and for Cohen's d. What we have to figure out is how to get this standard deviation thing, because we haven't calculated any standard deviation for the pooled samples. So how do we get that? What you have to remember is that standard deviation is the square root of the variance. Standard deviation is the square root of the variance. You can see it in the symbols, right? Something squared, something not squared. So how do I get from there to there? Well, just take the square root of it, right? Take the square root of a squared thing and you get no squaring. It's unsquared, which is not the same thing as rounding. Just so you know. Math jokes. Okay. So, it's pretty ridiculous. She's losing it over there. She's like, that was ridiculous. You just got it? She's like, oh, I just got it. Rounding is different than unsquaring. We're unsquaring now. Okay. So, what was our pooled sample variance? 12.13. So what's the square root of 12.13? 3.48. Yes? Okay. So that means 3.48 goes in the denominator up there. And what is 4.33 divided by 3.48? 1.24.
Yeah.
Okay. So our Cohen's d is 1.24. Now, to figure out whether that's a small, medium, or large effect, we need to look at the information provided in our overview. On the second page of that overview for this test, you'll see there's Cohen's d. And it says we're going to do some kind of sample mean difference over the pooled standard deviation. And then it gives us these ranges. And anything over 0.8 is considered large. So this is a large effect.
Where is that page?
Okay, so it's in this. If you go to the t-test for 2 independent samples, the stapled one, go to the second page. Second page. Now, this is the kind of thing that if you don't memorize it, you should put on your note card. have this on your note card because you don't want to forget what the ranges are for small, medium, and large, because you will be calculating effect size and you don't know whether I'm going to ask you to do Cohen's d or r squared on the test. So you want to make sure that you have this information on your note card. So we have 1.24, definitely a large effect. Now, r squared, another measure of effect size. R squared, in its most general form, is t squared over t squared plus degrees of freedom. Okay, that's the general formula for r squared. What you need to know for independent groups t-test is that this degrees of freedom is the same degrees of freedom we use to look up the critical value. In other words, it's degrees of freedom pooled. T in these cases, the t that we're squaring, is the t that we calculated. So this t and this t are t observed. Not t critical, t observed. Not the one we looked up, but the one we did the math to get. So that t observed was 2.15. So square that over 2.15 squared plus our degrees of freedom pool was 10. So what's 2.15 squared? 4.62. Okay. What is 4.62 divided by 14.62? I'm hearing two different numbers, 0.32. 0.32. Is everybody okay with all these numbers?
Yes.
So 0.32 or 32%. And if we look at the chart, we see that an r squared of 32% is large, also large. The two measures of effect size should give you pretty similar evaluations of effect size. If one is very large, the other one should also be large. They should be consistent. Because the effect size is the effect size is the effect size. Right? Now, do you guys remember what effect size is?
No.
Okay. See, brave soul. No, I don't remember. Okay, so effect size has to do with how much of an impact the independent variable had on the dependent variable. So think of it this way. We got large effect sizes here. What that means is children really, really like having their name in the book. It really influences their behavior. It makes a big difference. A small effect, when you have a small effect size, it means it made a little bit of a difference. But a large effect size means whatever our manipulation was, it was a big deal. Now, it's possible to get statistical significance with a small effect or a medium effect or a large effect, but it's much harder to get statistical significance with a small effect. When you have a really big effect size, it's going to be a lot easier to get significance. It's also, when you have a really big effect size, it's hard to miss it. That's important. It's hard to miss it. And missing is type 2 error, right? When you miss an effect that's really there, that's type 2 error. So when you have a really large effect size, you have a much smaller risk of type 2 error. because it's really hard to miss a gigantic effect. It's tough. But the smaller the treatment effect gets, the riskier it is. So the way you deal with that is you increase your sample size. You check more often. So that's why we want to have large samples, because large samples make it easier for us to see small effects. If you've got a monstrously big effect like the one here, you can do this with samples of size 6 and it's not a problem. You can see it, no problem, and get significance. You won't miss it. But the smaller an effect is, the bigger your sample needs to be for you to catch it. Does that make sense? So, let me check our time. Okay. So, the last thing on here is to summarize our results in one or more complete sentences, including an APA-style statistical statement at the end. When we do our summary of our findings, we want to follow the same steps we did before. These same steps. We want our summary of our results to have all that information. So we can say, based on our analysis, we rejected the null hypothesis, we got a statistically significant result, it was in the predicted direction, right? So we can say that children who read a story with their name in it read for a significantly longer period of time than children who read a story without their name in it. Notice how much that looks like the alternate hypothesis. Because that's all we're doing. We're just accepting the alternate hypothesis. We've rejected the null, and that leaves us